The de Broglie's dual behavior of matter and Heisenberg's uncertainty principle gave birth to a completely new branch of science called quantum mechanics. Classical mechanics successfully explains the behavior of macroscopic objects, such as falling stone, on the basis of particle nature. It ignores the concept of the dual behavior of matter and thus fails to explain the behavior of microscopic particles, such as protons, electrons, and so on. On the other hand, as quantum mechanics is based on the wave properties of matter, it describes the behavior of microscopic particles in a much better way. Hence, quantum mechanics is a theoretical science that helps to study the motions of the microscopic objects that have observable wave-like and particle-like properties. Quantum mechanics was developed independently by Werner Heisenberg and Erwin Schrödinger in 1926. The fundamental equation in quantum mechanics is Schrödinger's wave equation. In quantum mechanics, the mathematical expression which describes the wave motion associated with a particle is popularly known as Schrödinger wave equation. It gives the probability of finding an electron at different points in an atom. The Schrödinger's wave equation is obtained by differentiating the equation for the standing wave of an electron in the hydrogen atom. In short, Schrödinger wave equation is written in terms of Hamiltonian operator as shown here. In this equation, E stands for total energy of the system, which includes kinetic energies of all the subatomic particles and potential energy due to attractive and repulsive forces operating in an atom. When Schrödinger wave equation is solved for an electron of an atom, such as hydrogen atom, it gives the values of the possible energy levels in which the electron can move, called quantized energy states, as well as the wave functions corresponding to these energy levels. Note that, in quantum mechanics, all the properties of a system are expressed in terms of a wave function. This is obtained by solving the Schrödinger's equation. The wave function, psi, is a mathematical function that represents amplitude of the wave. It does not carry any physical significance. Therefore, the square of the amplitude of electron wave, that is, psi square, gives the probability of finding the electron at a point within an atom. That is why the function psi square is called probability density and is always positive. By finding the probability density at different points in an atom, one can predict the region of space around the nucleus, within which the probability of finding the electron is the maximum. This three-dimensional space around the nucleus, where the probability of finding the electron is maximum, is called orbital. This is why the wave function for an electron in an atom is also called orbital wave function or atomic orbital. An electron can have multiple wave functions and therefore multiple atomic orbitals. Schrödinger wave equation can successfully explain all aspects of hydrogen and hydrogen-like species. It, however, cannot be completely solved for multi-electron atoms. Such calculations show that the orbitals of multi-electron atoms are similar to the orbitals of hydrogen atom in most aspects. The principal difference between the orbitals of single electron atoms and the orbitals of multiple electron atoms is that the orbitals of multi-electron atoms are contracted due to increased nuclear charge. In addition, Unlike orbitals of hydrogen or hydrogen-like atoms, whose energies depend only on the principal quantum number, the orbital energies in multi-electron atoms also depend on azimuthal quantum number, in addition to principal quantum number. Let us now move on to certain other important aspects of the quantum mechanical model of atom. According to this model, electrons can only have specific values of energy, which means that the energy of electrons are quantized. The quantized energy values that result from the wave-like properties of electrons can be calculated along with the associated wave functions, psi, using the Schrödinger wave equation. The quantum mechanical model of atom supports the Heisenberg's uncertainty principle and says that one can only determine the probability of finding an electron at different points in the atom, but not its exact path. The atomic orbital for the electron is given by its orbital wave function psi. There are multiple atomic orbitals in an atom, as an electron can have many wave functions, each of which contains a maximum of 2 electrons. In a multi-electron atom, the electrons are filled in various orbitals in the order of increasing energy. Note that these orbits are 2-dimensional circular paths around the nucleus, in which the electrons revolve, whereas atomic orbitals are 3-dimensional regions around the nucleus, where the probability of finding an electron is the maximum. Now let us see how the atomic orbitals are distinguished by quantum numbers. On solving Schrödinger wave equation for hydrogen atom, the solution gives quantized energy states and the wave functions which are characterized by a set of 3 quantum numbers, which are the principal quantum number, the azimuthal quantum number, and the magnetic quantum number. An atomic orbital of an atom is characterized by these 3 set of quantum numbers. Orbitals are distinguished from each other on the basis of shape, size, and orientation. The probability of finding an electron depends on these 3 distinguishing characteristics. Such orbitals are again distinguished by 3 quantum numbers, which are, again, the principal quantum number, the azimuthal quantum number, and the magnetic quantum number. A 4th quantum number, called the spin quantum number, was also introduced later to represent the spin of the electron about its axis. Spin quantum number is characteristic for an electron. Therefore, quantum numbers can be defined as a set of 4 numbers that provide the complete information about the electrons in an atom. Let's understand these quantum numbers in detail. The principal quantum number, denoted by the letter n, determines the size and, to a large extent, the energy of the orbital in which the electron resides. The size of an orbital increases with the increase in n. In other words, the larger the value of n, the greater is the distance of the electron from the nucleus. An electron needs energy to move to the higher energy levels, as it has to overcome the forces of attraction from the nucleus. Hence, the energy of an orbital increases with the increase in n. Note that, for hydrogen and hydrogen-like species, energy as well as the size of an orbital depends only on n. In addition, with the increase in the value of n, the number of allowed orbitals increases and are given by n square. Shells are denoted by the capital letters K, L, M, N, and so on for the values of n equal to 1, 2, 3, 4, and so on respectively. The number of electrons in a shell is given by 2n square. Therefore, for n equal to 1, there will be 2 electrons in the K shell, and for n equal to 2, there will be 8 electrons in the L shell. The number of electrons in M and N shells will be 18 and 32 respectively. As the energy increases with the increase in N, the energies of the various shells follow the sequence K less than L less than M less than N less than, and so on. Let us move on to the next quantum number, that is, the azimuthal quantum number. It is denoted by the letter L. The number of subshells is given by the azimuthal quantum number. The azimuthal quantum number is also known as the orbital angular momentum or subsidiary quantum number. The azimuthal quantum number also describes the three-dimensional shapes of orbitals that you will learn about in the next module. For a given value of the principal quantum number n, the azimuthal quantum number L can have n values ranging from 0 to n-1. The value of L, in turn, defines the number of subshells, which means that when n is equal to 1, L is equal to 0. That is, there is only one subshell in first main energy level. Similarly, for n is equal to 2, L is equal to 0 and 1. That is, there are two subshells in second main energy level. And for n is equal to 3, L is equal to 0, 1, 2. That is, there are three subshells in third main energy level. Subshells corresponding to different values of L, that is, 0, 1, 2, 3, 4, are represented by the symbols S, P, D, F, G, and so on. The first four notations are the initial letters of the words sharp, principal, diffused, and fundamental, the words formerly used to describe different spectral lines. Thus, the subshells in the K shell for n is equal to 1 is S. In the L shell with n is equal to 2 are S, P. In the M shell for n is equal to 3 are S, P, D. In the N shell for n is equal to 4 are S, P, D, F, and so on. The S subshell has the lowest energy, and the energies of the subshells within the same principal shell follow the order S less than P less than D less than F. An electron moving in a subshell generates an electric field and magnetic field resulting from its motion around the nucleus. Thus, under the influence of an external magnetic field, the electrons moving in the subshells tend to reorient themselves into the specific orbitals. The number of preferred orientations of electrons belonging to a subshell is given by another quantum number called the magnetic orbital quantum number ml. Each orientation corresponds to an orbital. Therefore, magnetic quantum number helps to determine the number of orbitals within each subshell. For a subshell, there can be a maximum of 2l plus 1 preferred orientations or orbitals with values ranging from -l to +l, including 0. Hence, for L is equal to 0, the number of preferred orientations is equal to 1. Thus, S subshell can have only one orientation in space and only one orbital. For L is equal to 1, the P subshell can have a maximum of 3 orbitals with orientations along the 3 axes. Similarly, for L is equal to 2, D subshell has 5 preferred orientations and hence 5 orbitals. Using the same calculation, F, G and H subshells can have 7, 9 and 11 orbitals each. Note that all orbitals belonging to a subshell have the same energies and therefore are called degenerate orbitals. Thus, the 3 quantum numbers can very well define the energy, shape and orientation of atomic orbitals. However, these quantum numbers fail to explain the presence of closely spaced lines, doublets or triplets in the atomic spectra of multi-electron atoms. To explain these lines, in the year 1925, George O. Beck and Samuel Goudsmit introduced the 4th quantum number called the electron spin quantum number or MS. The two scientists suggested that just like the planet Earth, an electron rotates around its own axis while revolving around the nucleus. The electron spin results in an intrinsic spin angular momentum that can have 2 possible orientations, clockwise or anti-clockwise, relative to the chosen axis. These orientations are defined by the spin quantum number ms that can take the values of +1/2 and -1/2. These values are represented by upward and downward arrows and are called spin up and spin down respectively. The 2 electrons belonging to a particular orbital always have opposite spins.